Hello, welcome to another module in this massive open online course. So, we are looking at the Z transform, its various properties. Let us start looking at some example problems to better understand the applications of Z transform. Okay, so what we want to do starting at in this module is we want to look at several example problems to better understand the properties and the applications several properties and the applications of the Z transform. Okay. So, let us look at the first problem. For instance, consider xn equals an, 0 less than or equal to n less than equal to capital N minus 1 and equal to 0 otherwise. That is xn equals an for 0 less than equal to small n less than equal to capital N minus 1 and it is 0 otherwise. We want to find the Z transform, that is find the Z transform x of z along with the poles and zeros. Now, the Z transform of this can be evaluated as follows. Remember, the Z transform x of n equals summation n equals minus infinity to infinity xn z raised to minus n, which in this case will be summation n equal to, because this is non-zero only for n lying between 0 and capital N minus 1. So, this n equals 0 to n minus 1 an z raised to minus n, which is summation n equal to 0 to n minus 1 a z inverse raised to the power of n, which is equal to, using the properties of the summation, this is 1 minus a z inverse raised to the power of n divided by 1 minus a z inverse. That is the Z transform. Okay, so this basically is the Z transform. Okay, and I can simplify this as follows. I can simplify this, that is x z. You can also write this as z power n minus a power n, that is multiplying numerator and denominator by z power n by a power n by z minus a into 1 over z power n minus 1. So, there is also another way to write it. And now you can see the pole, the zeros correspond. Now, the pole is at, now let us first look at the poles. So, this has poles at z equal to a, and you have this term z raised to n minus 1, which means this has a pole, that is n minus 1 poles, or pole with multiplicity n minus 1, because you have z raised to the power n minus 1 in the denominator. It means that you have pole of multiplicity n minus 1 at z equal to 0. So, z equal to 0, you have a pole of multiplicity n minus 1. Okay. Now, let us look at the zeros. Now, zeros are very interesting. In fact, if you look at zeros, zeros are obtained by solving this equation, z raised to the power of n equals a raised to the power of n. You can write it, in fact this is equal to a raised to the power of n into 1. So, z can be written as a raised to the power of z equals a times the nth root of unity. So, times e power j 2 pi k over n, correct, where e raised to j 2 pi k over n is one of the roots of unity, one of the roots, nth roots of unity. Is one of the roots of unity, one of the nth roots of unity. That is, this is a solution to the equation 1 equals, or this is a solution to the equation x raised to the power of n equals 1, nth roots of unity. That is the solution of x raised to the power of n equals 1. Okay, so that is e raised to j 2 pi. So, the poles are zeros are e power j 2 pi k n over n, where k equals 0, 1 up to n minus 1. Now, if you set k equal to 0, now for k equal to 0, you have 0 at z equal to a. So, basically if you observe, you have a 0 at z equal to a, correct. Remember earlier we have seen that you also have a pole at z equal to a. So, the 0 and pole at z equal to a cancel, alright. So, what you are left with is basically 0 of multiplicity, that is zeros are basically nth roots of a e raised to j 2 pi k over n, k ranging from 1 to n minus 1, and pole of multiplicity n minus 1 at 0, because the pole and 0 at z equal to a cancel. So, what you have is basically pole and 0 at z equal to a cancel. So, what is remaining is you have the unit circle, and you have the poles which are placed equidistant, correct. So, you have the poles which are, for instance, these are the zeros which are placed equidistant. So, you have the zeros and so you have, what you have is zeros are equispaced on unit circle, zeros are equispaced on the unit circle, and you have a pole of multiplicity n minus 1 at 0. So, this is n minus 1 zeros, n minus 1 zeros equispaced on unit circle, and pole of multiplicity equals n minus 1 at z equal to 0. And here, mind you, at z equal to 0, you have pole and 0 cancellation. They have at z equal to a. I am sorry, this is a circle of radius a, not unit circle. This is equispaced on circle of radius, equispaced on circle of radius equal to a, and at this point a you have pole 0 cancellation, that is the pole and 0, the pole and 0 cancel at z equal to a. So, that is basically how the pole 0 plot of this. So, net we have poles. So, net we have zeros e raised to j 2 pi k over n, k equals 1 2 up to n minus 1, and poles you have at 0, pole at 0 of multiplicity n minus 1. Okay. So, you have pole at 0 of multiplicity n minus 1. That is how the pole 0 diagram of this of the Z transform of the given signal looks like, okay, which is a raised to n for 0 less than equal to n less than equal to capital N minus 1. Okay. All right. Okay. And let us look at the next problem, that is x n equals 1 over 3 raised to the power of n u n plus half raised to the power of n u of minus n minus 1. We are required to find the Z transform of the given signal and naturally also the associated ROC. And for this, remember Z transform and also sketch the pole 0 plot, find the pole zeros and pole 0 plot. Also we want the pole 0 plot. So, we require to find the Z transform of this given signal and also find the pole 0 plot. Okay. All right. So, now to do this we are going to use the following result. We will use the result that what are the result that we are going to use? We are going to use the result. So, these are the results A n u n, this has a Z transform Z over Z minus A, but the ROC is magnitude Z, this is a right handed signal. So, ROC is magnitude Z greater than and a to the a raised to n minus u of minus n minus 1 or minus a raised to n u of minus n minus 1, this as the Z transform Z over Z minus A, and the ROC is, this is a left handed signal. So, the ROC is of the form magnitude Z less than A. So, now if you look at this, you will have 1 raised to 1 over 3 u n, this as Z transform Z over Z minus 1 over 3 and half to the power of n u minus n minus 1, you can see it has Z transform minus Z over Z minus half, because minus half raised to n u minus n minus 1 has Z transform Z over Z minus half, half raised to n u minus n minus 1 has Z transform, that is minus of Z over Z minus half, and the net Z transform of the given signal is the sum of these two components. So, the Z transform, that is your signal x of Z, is therefore Z over Z minus 1 by 3 minus Z over Z minus half. Now, the ROC of this is, ROC of the top one is magnitude of Z greater than 1 by 3, ROC of the bottom one is magnitude of Z less than half. So, the ROC of this is basically the intersection of these two, that is magnitude of Z greater than 1 by 3 intersection magnitude of Z less than half, which is basically equal to the region half or 1 by 3 less than magnitude of z less than half. This is the ROC. And the z transform can be simplified as, that is z over z minus 1 by 3 minus z over z minus half, that is z into minus 1 by 6. Okay. So, minus half z plus 1 by 3. So, z into minus 1 by 6 divided by z minus 1 by 3 into z minus half. Okay. And therefore, this is equal to the net z transform x of z equals minus 1 by 6 divided by z minus 1 by 3 into z minus half, and therefore, we have the ROC is 1 by 3 less than, and then ROC, this is the z transform. Of course, the z transform is incomplete without the ROC. So, the ROC is 1 by 3 less than magnitude of z less than half, and therefore, if you draw the region of convergence on the z plane, it looks something like this. So, the poles are at, so 0 at, you can see it is z over z minus 1 by 3 into minus z minus 1 by half. So, 0 at z equal to 0, the poles are at z equal to 3, z equal to 1 by 3, and the ROC lies in between these two poles. Remember, this is a two sided signal. So, ROC is of the form R1. From your properties of the ROC, you will realize that ROC is of the form R1 less than magnitude of z less than R2. Okay. So, I am not able to draw this concentric circles, just apologize for this. I think that will have to do. So, what we have over here is, let us say we call this 1 by 3 is equal to, so this is the real part of z, this is the imaginary part of z. Okay. This, there is a 0 at 0, and there are two poles, one at 1 over 3, one at 1 over half, and the ROC is basically between the two poles, that is between the concentric circles corresponding to the two poles. Okay, z plane. Poles equal to 1 by 3 comma half, 0 at 0. Okay. So, this is what the z transform. So, ROC, so this is the pole 0 plot. So, this is the pole 0 plot, this is what the ROC looks like, and this is basically the z plane diagram. Okay. And the ROC comprises of basically the region between these two concentric circles. One is a concentric circle corresponding to magnitude of z equals 1 by 3, the other is the circle corresponding to magnitude of z equals half, and the ROC basically corresponds to the region between these two concentric circles. Alright. So, this is basically how the ROC corresponding to this problem looks like. Let us do one more problem in this module, and then we can continue later. So, this is the z transform. So, find the z transform of, now this basically it illustrates a property a power n plus 2 u power n plus 2. Now, consider, to find the z transform of this, consider x tilde z, x tilde n, a different sequence, that is a power n into u n. You can see that x n is x tilde of n plus 2, that is time advanced version of x tilde, that is x tilde advanced by 2. So, x n obtained by time advanced version of x tilde n. Time advanced version of x tilde n. And now if you take the z transform of x tilde n, we know the z transform of x tilde n, that is x tilde z equals z over z minus a. Now we have x n is x tilde n plus 2. So, x of z we know is z square by the time shifting property, z square x tilde z, that is z square into z over z minus a, that is z cube by z minus a, and the ROC will be, since this is a right handed signal, ROC will be magnitude of z greater than a or magnitude of z greater than magnitude of a. Okay. So, ROC is magnitude of z greater than magnitude of a, and the z transform is x z equals z cube over z minus a. So, that is the z transform of this signal. Alright. Okay. So, that completes this problem. Alright. So, we will wrap up this, let us wrap up this module with this problem, and we will look at other problems in the subsequent modules. Thank you very much.